Thank you very much, everyone. Thank you very much to the organizer of these interesting events and very stimulating. So today I will talk about our proposal to improve privacy of Bayesian networks. One possibility, in particular, we propose a Credal network for achieving this goal. However, the work is, I have first to say that, to disclose that this is the main research work from Niccolò Rocchi, a PhD candidate in computer science at the University of Milano Bicocca, and is funded by the National Institutes of Tumors, and this obviously has links with respect to the topic that we in general study. And it is also a joint work with Cassio De Campos from the University of Eindhoven in the Netherlands. Having said that, I just need to give the framework because of the fact that the fellowship of Niccolò Rocchi is funded by the National Institute of Tumors. We are mainly interested in answering clinical queries in the case of rare cancers. And in these cases, it is important that you are in the condition to describe the evolution of the cancer from the point of view of the patient, because you aim substantially to evaluate which are the factors evaluating the prognosis of the patient, and possibly you want to assess the effectiveness of the treatment. We have several issues here with this type of data. We have sparseness, we have many selection different types of bias, in particular selection bias. We suffer from missing data, in particular missing data not at random due to the practice of the medical doctors. Then the point is that under this condition, we make a decision to use Bayesian networks because they give some features that are relevant to interact also with medical doctors. They allow to model data generating mechanism. They allow to include expert knowledge directly to embed their domain knowledge into the model, and they deliver somewhat explainable predictions. And if we also make the strict causal assumption about the edges, then we can also use them to make decision and possibly to compute or at least to estimate counterfactors. Here to the right, you see Bayesian networks. An example, you have several nodes. Every node is associated with a variable that has a semantic. They are typically binary or multi-nomial variables. This model has been developed by combining the knowledge from the oncologists, in particular soft tissue sarcoma oncologists from the National Institute of Tumors, and the data that is available. Okay, so what about Bayesian networks? Just a refresh, Bayesian networks are probabilistic graphical models. They come with two different components. One component is a directed acyclic graph that we call calligraphic G, and with a set of probability distribution. In particular, we are interested into discrete variables, so substantially we are talking about conditional probability tables in that case. One of the main features of Bayesian networks is that they allow you to factorize in a very compact manner the joint probability distribution. So P of X can be factorized, only taking into account for each variable that you have the conditional probability of that variable given the set of parents. Just to clarify, the set of parents is the set of nodes that have edges entering into other nodes. So for example, size and grade are parents of radiotherapy. Okay, so one possibility in the healthcare system, because we have rare data, we have rare cancer and so on, so we have very few data. Typically what's happened is they develop what is called multi-center studies. So you get the data from several hospitals, yeah, and then you try to increase the sample size to increase the power of what you discover. However, this comes at the cost that obviously now you are in a trouble, because if you pull all the data together, or even assuming that you can manage different biases coming from different hospitals, if you put all the data together and you move the data into a centric manner, then you start to have severe privacy issues. So it is very, I mean, hospitals really do not like to share their data for many, many reasons. Sometimes it happens because the data is not really high quality, or it is not in the proper format, and so on. But this simply prevents them to see the contribution of the data as a potential option. Today we have an alternative, which is rising, which is the one of federated learning. In that case, substantially, the data stays at the centers. The center develops their own model, they learn the model, and they do not share the data, but share the models. However, also this approach has obviously some privacy concerns. So also if you share the model, you are not sure about your privacy. In this case, what may happen is that an attacker, substantially, when you make available your Bayesian network model, trained on a given center, so using private data, then the attacker has access to the Bayesian network model, and it also can use public data, what is called their open data. And it may be concerned with attacking, trying to steal some information about individuals being included into the private data set, so the data of the specific hospital. In particular, the schema is like this. So you have the Bayesian network that has been learned using the private data, calligraphic T, and the attacker has access to this model because the model has been made available to be used, obviously, and it can also use the general data, the public data, and it substantially estimates it knows the calligraphic G, so the structure of the model, and it simply uses the public data to estimate the parameters in a different manner. And now the goal, for example, in this case, maybe if you take into account a Maya attack, which is the membership inference attack, the attacker wants to discover whether an individual from this set of data has been included into the data T. So if it contributed to develop the model. That's the main idea. And the attack goes like this. So the attacker performs an hypothesis test with H0 and H1 just to check whether the individual that has been sampled from the set of the data that are publicly available is included or not into the private data set. And typically, the statistic that is used in that case is L of X that you see there, which is the difference between the log likelihood of the observation on the two different values of the parameters. So the theta at T, which is the parameter that has been made available by those who learn the model, and theta hat R, which has been estimated from the general population. And if this value, L of X, is greater than a given threshold, then the attacker will conclude that the individual X from the general population has been used to train the model, to train the Bayesian network model. So in some sense, it is successful. So it discovered that individual was included into that data. So there is an important result from Murakond et al. That provides a link between the power and the type 1 error of the attacker. The type 1 error is substantially the probability that the attacker concludes that the individual is substantially into the set while it is not, and the beta power is the other. So the capability to discover that the individual is into the set when indeed it is into the set. So substantially beta is the probability for the attacker being successful. And typically it works like this. The attacker accepts the risk alpha, the type 1 alpha, and then want to maximize the beta, the beta value. So substantially the power of the attacker. And in the Murakond theorem, it is proved that there is a strict dependence between the type 1 error alpha and the power beta, which is ruled substantially by the complexity of the graph and by the cardinality of the data set that is used by those who train and made available the Bayesian network. Okay, this is just a very rough example. If this is our Bayesian networks with just 3 nodes, and we take into account only binary variables there, substantially you have the black numbers into the tables, and you have the blue numbers into the table. The black refers to the data set calligraphic T, which has been used to develop the network, and the blue are related to the general population. And substantially, the attacker, what he's doing is that he's computing this difference between the two logs, and if this difference is greater than a given amount, that is a threshold that you have set, and you set it by accepting the alpha type 1 error, then substantially it concludes that that specific element, in that case 000, has been included into T, and so substantially it is successful in its attack. So, however, we can obviously try to reduce the success of the attacker by simply adding some noise. And we can add the noise to the joint probability of each random variable together with its parents. And obviously, because of the factorization, then we can simply translate such a noise, which is of a Laplacian type, into the, again, back into the conditional probability distribution. So, however, this may be an option, yeah, to take into account. But the problem here is that substantially, if you do this, if you add this term, this eta term, then it is no longer guaranteed that your Bayesian network factorizes according to the same conditional distribution as the original Bayesian networks. Furthermore, you also have a loss of accuracy when you use the model, obviously, and somewhat you abandon mainly entirely the possibility to have an interpretation because of the noise. Okay, so now I come to our approach. Our approach is to use epistemic uncertainty through what is called Credal networks. And Credal networks substantially help us to mask the Bayesian networks in a different manner rather than the noise injection. And so because they have theoretical properties, for example, it has been shown that a Credal network yields correct inferential bounds, so it is reliable and it is interpretable, one of the two properties that we were losing substantially. Then we investigate this model, and here to the right you see this triangle, gray triangle, is the set containing all probability distribution for a random variable which can take three different values, so x1, x2, and x3. And the blue point is substantially the probability that is associated with the Bayesian network that you are making available, so the one that you have learned on the calligraphic T data set, while the red point is substantially what has been learned, estimated by the attacker substantially. And say the point is that, so you substantially noise, you add the noise and you move from there up to here. But you see that what we propose is not to do this, but to use the Credal set, which is implied by the Bayesian network that you are learning. And this is the salmon colored triangle that you see there. So inside of that triangle, we say, okay, we have the true probability distribution, but we don't say anything more about that. So just to better frame what Credal networks are, here we have a formal definition. A Credal network is the same as a Bayesian network in terms of the qualitative components. So the graph has exactly the same meaning, but then instead of having a probability distribution, instead of having a single probability distribution, we have an entire set of family of probability distribution that are called the Credal set. However, the Credal set, we made the decision to use the definition of such Credal set, which is extremely complex to be specified if you take into account high-dimensional vectors. We made the decision to specify this Credal set in a local manner. So for each random variable, we specify a Credal set, and we made it independently or irrespectively of the Credal set of the other nodes. And to define such Credal sets, obviously here we are imposing that obviously this condition is true. So again, we are enforcing that the probability distribution must factorize according to the Bayesian network. So substantially, we are fulfilling the tree. We are coping with the tree limitation that originate from the noise injection. And to build such Credal set, we use the imprecise Dirichlet model, which has a parameter S that substantially tune the level of uncertainty that you include into your model. Okay, so substantially this is the point, and now the attacker, you make available the Credal networks, and the attacker now is no longer using these probability estimates on just on the R set of data, but because it knows this is the Credal set, it attacks you at least by fulfilling the constraint, because it knows that the true probability is there, and so it will use the maximum likelihood estimation, but constrained to be inside of the Credal set. So substantially, it selects the theta at R k, which is substantially the maximum likelihood constraint to be into the Credal set, and then it designs a new statistic, which is no longer L of x, but it is L of x prime, where the only difference is that now you are using that estimate. We prove the consistency of the attacks. That simply tells you that if the attack against the Credal network concludes that the individual X belongs to the private population, then so would the attack against the original BN. So there is no, so at least we do at least as good as the BN. And the same applies to the alpha and beta in the sense that if the attacker set an alpha value, then the beta, so the power of attacking substantially using the Credal network, is not larger than the power if you attack the original Bayesian network. So again, in this case, we prove that we are not inferior to that. This is the general schema of the new situation. The things that you have to pay attention is this L prime, which is replacing before the L of x. And now I just want to give you some results of the experiment that we have performed. We have performed experiments by changing the number of the variables, by changing the number of the edges, so having different level of density. And the CG is substantially the numerator of the Murakonda bound that you have seen before. So in an ideal situation, we have here the alpha, so the type 1 error, and then we have the power, and this is the point of view of the attacker. So the dream of the attacker is to have something like this, because then for very low alpha, very low risk, then it is capable to be very, very successful. And we have the Bayesian network, which is the red line, and then we have our Credal networks with different values of the parameter S. And you see that if we set the value S to 100, we have almost the optimal possibility, because we have a 45 degrees line that is telling that you cannot do any better than that. However, we also compared to the Laplacian noise injection. And in this case, we have S, which is the parameter that is ruling the degree of uncertainty that we are using. And there to the left, we have substantially a measure of the accuracy. So how useful is the model that you are making available after having added some privacy? So in a sense, you are saying, which is the cost of ensuring privacy in terms of the utility of the model. And you see that substantially the Credal network approach is quite stable. It is working quite well, while the noise injection using Laplacian methods is degrading quite soon. How can we build this graph? We simply match the S with the epsilon of the Laplacian n, and we did it by matching with the area under the curve of the different approaches. Okay, so however, we have limitations. We just investigated one type of attack, so many other may be designed and taken into account. we miss sharpen and close form results of finite samples. So, Nicola, there is work for you if you want. And we only evaluate on synthetic data, and so we really want to move on also on real data. The last step is that because we were interested into federated learning, now we are extending all this stuff in the case where we are in a true federated learning. So no longer one model to be shared, but several models are traveling across the federated situation. Okay, so if you are interested, you can find the paper with this QR code. And I would conclude by thank you all of you, and obviously my co-authors, Nicola Rocchi and Cassio De Campos. Thank you very much.
Great question. Yes.
Well, as you said, assuming some attack type is really necessary in this kind of research, but isn't this really critical? Because attackers, if know this, then they will of course find another way to attack the system.
Yes, you are right, but yes, of course, I understand your point. So you say it may be the case that they are using a different attack and protect with respect to one, but they are using another, and so they are successful. Yes, this is perfectly, it makes a lot of sense what you say. So this simply means that we have a lot of work to do. from my
but isn't this more like an endless game? Because if you have something new, the second one, then attacker knows, okay, there's a second one, then let's develop third one. And so this continues forever.
It means that we can develop a lot of research. But I understand, yes, it is, of course, we have to make some hypotheses about who is the opponent. And also, you have to take into account that we are sharing, that we are using that model. If we are not sharing, for example, that we are using Credal sets, then obviously it is again in an issue also the individual.
So isn't there a kind of high level view of this kind of framework? Because if you consider specific attack, then attacker can know this and then they can do something else. But if you have some class of attacks or something, then attackers in this class cannot.
But it may be the case that the same strategy allows to manage different types of attack. It is not, I mean, obviously there may be more wise, and indeed it is the limitation that that I mentioned in the last slides. We are just at the beginning of studying this behavior.
That's quite challenging. Thank you very much.
Plenty of time.
Let's thank again the speaker.
Thanks for the introduction. And thank you for this great opportunity, and thank organizers for this wonderful workshop. This talk is about adaptive learning rate for Follow-the-Regularized-Leader, and this talk is based on this paper. And this talk is about online optimization, online learning, and regret minimization. So we are focusing on online learning setting and how we can minimize our regret. There are many reasons why we are interested in regret, including the connection to stochastic optimization and application to many other fields, including reinforcement learning and game theory. The most basic algorithm for online learning would be online gradient descent. I'd like to skip the detail, as I believe you are very familiar with this. But given this online gradient descent, we can get this upper bound for regret, given the learning rate eta, right? So we have a question how to choose the learning rate eta. The typical choice for eta would be this one. This minimizes the right-hand side. And this is actually optimal in terms of worst-case analysis. But if we want to minimize this one, the intermediate formula, the optimal choice will be given by this formula. Given this, we can get upper bound depending on the norm of gradient. So this is better, especially when the gradient is small in chance, but an issue that is that this choice is impossible to implement in practice because we don't know the gradient norm in advance. Okay, so this is a bad news, but there is a well-known solution to this issue. That is just choosing the adaptive learning rate depending on the gradient observed so far. Right? In the previous slide, we choose eta fixed so that it depends on the old gradient, but just by choosing the gradient based on the gradient observed so far, I think this is a very natural choice, and we can show that it's clear that this can be computable from the past observation, and surprisingly, this can achieve the similar gradient norm-dependent upper bound like the previous slide. And this type of learning rate tuning method is called Adagrad type learning rate. I think Adagrad is very well-known term in the context of optimization field, but there is in the field of online learning, earlier work provide a similar approach of tuning learning rate in earlier works in online learning field, including Nicolo. So I'd like to, and under the name of self-confident online learning. So I prefer using this term for now. So let's move it on to the Follow-the-Regularized-Leader. In Follow-the-Regularized-Leader, Follow-the-Regularized-Leader is a generic framework for online learning in which we minimize this objective function composed of objective function observed so far and with additional term of regularizer. And we can see that for specific choice of regularizer, we can recover the gradient descent. And it also recovers well-known exponential rate method when we consider this method over probability simplex and entropy regularizer. So this can be considered as a general framework, including many important examples of online learning method. And this has been used in many online learning programs, including multi-armed bandits, and that's generalization. Similarly, in the case of online gradient descent, the upper bound for the regularized FTRL achieves this type of upper bound, which can be given as the sum of which we refer to as stability term and penalty terms. Where ZT depends on the problem setting and regularizer, and HT is also depending on the regularizer. The specific example includes, for example, in the case of online gradient descent, the stability term is given by the norm of gradient, and it may change depending on the problem setting. So, and basically, there is a kind of a trade-off relationship, increasing learning rate makes stability terms bigger, and for penalty terms makes it get smaller. Okay. So you can say that it's important to tune the learning rate to minimize this term. So, and similarly to the case of an online gradient descent, we can choose self-confident update rules like this one. And then we can get the regret upper bound depending on the stability term, right? Here, H bar is the upper bound of penalty terms. So we can say that this is adaptive with respect to the stability term ZT. But given this result, our natural question would be how we can, or can we make it adaptive with respect to the penalty term HT as well? So this is the main question of this talk. To this end, I'd like to start with the key property appeared in the proof of this learning rate update rule. One key inequality is that in this update rule, we can say that the single round stability term is bounded by the difference between the learning rate. Okay. We may start with this property. I mean, given this condition, we can reconstruct this. This implies that the learning rate is approximated by the case of a self-confident update rule. So, I mean, we can consider this as a starting point. Here we use H bar here, and a natural approach is for generalization is to replace H bar by HT plus 1. We can say this. We can interpret this as a we have another natural interpretation, like in this formula, there is we can interpret, we choose learning rate so that these two terms in trade-off matches, okay? So that's a natural approach to minimize the term under the trade-off relation. So in the following, I'd like to analyze what we can get in this under this learning rate. First, given this stability penalty matching approach, we get the learning rate like this. And for the special case, if HT is a constant or we replace this by uniform upper bound, we can recover the self-confident learning rates. And if HT is almost equal to ZT, then we can construct, we can recover the another standard learning rate of 1 over square root T. But I'd like to mention some technical challenge. Given this condition, we get the recursive update rule like this one. But to define eta t plus 1, we need to know HT plus 1, but this also depends on eta, so it's impossible to implement. But this can be resolved by simply replacing HT plus 1 with HT. This can be justified and when under this condition. Okay. So given this update rule, we get this results. First, we can get the regret upper bound depending on ZT and HT simultaneously. And this also recovers upper bound for self-confident type learning rates. So it's not worse than self-confident upper bounds, self-confident type upper bounds. Okay. So you may wonder when this new bound useful. The penalty, usually the penalty term can be illustrated as like this figure. So we can say that if xt approaches to an extreme point of x, then this penalty term gets smaller. So under such situation, we can get improved performance. So, and we can say that this is useful in the design of best of both worlds bandit algorithms, because in stochastic environments, the probability distribution approaches to an extreme point, and we can exploit such structure. Best of both worlds bandit algorithm is, let me briefly explain the best of both worlds. In the field of bandit algorithms, basically there are two different types of environments have been considered. Stochastic environment, in stochastic environment, loss is assumed to be IID, so stationary. On the other hand, adversarial environment doesn't impose such assumptions. So, and traditionally for studies in bandit algorithms, there are for these two different types of environment, different type of algorithms have been developed. But in practice, it's difficult to distinguish the actual environment, which the actual environment is categorized which one. So it's better to get a single algorithm achieving better performance both of these environments. So such algorithms are called best of both worlds. We can show that by using FTRL with stability penalty matching, we can construct a generic framework for constructing best of both worlds algorithms. We use the Thalys entropy regularizer over probability simplex. Then we can get two different types of upper bound. This implies that the regret is bounded by this term, and this provides a square root t type upper bound. And intuitively, under this construction, the regret is, when regret is smaller than the point xt, the probability of choosing arm approaches to extreme point of the simplex, and then this value gets smaller, so that we can get improved upper bound. The proof sketch is here is the actual what we get, and we can say that under the stochastic environment we can get log t regret. So this implies a best of both worlds. These approaches have can achieve. As I said, this provides a generic framework for designing the best of both worlds algorithms for various many different bandit problems. So far, the best of both worlds algorithms have been considered one by one, but this provides a generic approach using only FTRL by just tuning the learning rate. So I think that's an interesting point in my opinion. So this is a summary of this talk, and the paper also includes formal competitive analysis that the stability penalty matching itself the optimal in the sense of competitive ratio. And we have many future direction in mind. One is application to other problems and combination with parameter-free learning, online learning, and extension to multidimensional learning rates. Let me share some of my recent advancement. One follow-up result is about more complicated online learning. In some harder online learning problems like partial monitoring or bandit with graph feedback, the regret can be expressed as this form, including additional parameter called exploration parameter. We have shown that in this work, we have shown that even for these cases, just matching all terms can work well to get best of both worlds. And in this paper, one technical challenge so far is that making sure this condition hold is difficult. It's very technical point, but this paper provides a good general method for making sure this holds. And in this paper, we generalize the problem into heavy-tailed distribution case, and we also generalize the scope into follow the part of the leader. In this case, it's difficult to. One difficulty is that there is no explicit form of penalty and stability, but we can introduce a surrogate one to enable to apply stability penalty matching. So that is the end of my talk. Thank you.
Other questions?
There are ways to also account for optimistic version in this framework?
In this paper, we combine optimistic approach and stability penalty matching.
Okay. Thanks again.
All right, so let me begin my talk. So I'm Han from RIKEN AIP as well, and my main affiliation is called the Institute of Statistical Mathematics, which is also in Tokyo as well. So let me talk about the closer look at the implicit bias of the gradient descent today. And so, as the Masaki's talk as well, so we're very interested in the over-parameterization phenomenon in the recent deep learning things, and also that going to be happening in a more simpler settings. Like this is the synthetic experiments that I myself run, and actually there are a few points, like I guess over up to 20 points, the training points, and if we fit the polynomial of the function to disturb the small scale data set, so it's going to be very easy to overfit by using, let's say, in the left-hand side we have just solving the least squares. So the resulting regression function is pretty wiggly like this, and it doesn't make so much sense at all. But if we use alternative way to fit in the regression function, just for instance using the gradient descent to fit in the polynomial function. I mean, the functional class are totally the same. The algorithm we use are different to each other, just solving either the normal equation for the least squares exactly, or using the gradient descent to do the adaptive updates or not. So I hope the right-hand side is much more meaningful as a learned predictors. So even for the same the functional class that we use, there are obvious different the behaviors for the what algorithm that we use here. So we're gonna study when such sort of the overparameterized things are prevented or not. And such phenomenon is typically called like an implicit bias. And actually the terminology of the implicit bias is not quite well defined. So let me just explain sort of the tutorial and also in what sense did I use the implicit bias in my talk, throughout my talk. So, in the classical, the statistical learning frameworks, it is very typical to use empirical risk minimization plus some regularizer term like this. And the regularizer term, since we're minimizing the training risk, so it's going to be easily overfitting if we use the too expensive the models. But just using the regularizer, so it's just taking the trade-off between the the fitting to the training loss and the too much expressivity here. So it's a kind of the classical formulations. But implicit regularization is, you mean the contrasted with this explicit encoded regularization term. So this is not a regularization explicitly encoded in the objective like in the classical formulation, and it's just arising naturally without intention from the optimization dynamics, the optimizer's algorithm that we chose. Let's say we have this sort of the hypothesis space, and the blue shaded place are some sort of the perfect interpolators, and we assume this hypothesis space is already expressive enough to interpolate all of the data points here, and we just begin from the central like the blue points here, and just because we're doing the updates adaptively, so we're just evolving this one point here is just corresponding to the one specific function in the functional class, and it just evolves and reach to some boundary where we interpolate all of the training points. So since we're doing such sort of the dynamical the fitting using, for instance, either the gradient descent or something else, so it just evolves one by one to reach into the interpolation regime, so that it's not going to be super flexible like the very far function like in the expressive space, but it's just constrained to the very simple the places just like this. So basically, we can just regard this phenomenon as something like optimizers selectively chose a simpler solution, so they have such sort of the preference to over the all possible functional classes. So that's roughly called implicit bias. And this is already, still quite remain to be the intuitive explanation. So let me just give you one typical example of the implicit bias in the community, which is known as max margin implicit bias. So there are some setups here. So we're just considering, this is a super synthetic, the easy example here. We're considering the separable binary data just like this. So we are considering like the binary classification setups, so X, I, and the Y are the pair data set, and we have some W star, which is a true separator of these observed data points. And we just assume this is linearly separable so that all of the points can be separated with a strictly positive margin gamma. So gamma, I'm going to use the notation gamma later on repeatedly. So you can just, keep in your mind. So gamma will appear repeatedly. So the gamma is strictly positive margin to separate all of the training data point, and it is the data set dependent on the parameters. And what we do is that we consider linear classification risk capital L here, which is just like the average logistic loss here computed over the all possible linear separator. So the linear separator W is the functional class that we're considering right now. And the optimization is done by here. For simplicity, we consider the gradient flow, so dW dt, which is just following the steepest negative gradient descent the directions. And this is a continuous dynamics, but actually we can do the similar things even if after the discretization of this the ordinary differential equation. But since this is more easier to understand the dynamics here, so during the presentation, so let me or at least the first half of the presentation, I'm going to focus on the ordinary differential equation formulation like this. But you can just consider this persists in the gradient descent as well. And I just converted the template. So actually, the reference here is just like the white size. Yeah, it's not very clear to see. But anyway, over a decade ago, the Sudari et al., his colleagues in 2017 or I guess 18, show this beautiful result, so that under this very simple setups, the gradient flow evolves in this way. So you can just read the one by one. So the WT is the parameter that we're considering right now, and the T is just like a training steps, and it's the direction converges asymptotically to the W hat, which is the max margin problem written in the bottom line here. So W star is the separated separate all of the points, as well as minimizing the W norm like this. So this is a max margin solution, and the theorem states that our parameter after the asymptotic evolution, it converges directionally to this W hat. All right, so pictorially we can just view like this. So we have the training data set. So all of the points here are the training data set, and we have W hat looks like this. So which is a max margin separated like this, and after we have W0 beginning from arbitrary place, and we just evolve following the gradient. I mean the landscape here just illustrate the gradient of the flow, the loss landscape, and after the asymptotic time, so they just follow this direction, the W hat direction asymptotically. But of course we're considering logistic loss, so the norm of the W T just blows up to the infinity. But if we look at the direction, then the directional converge happens like this. So that's what's going on in here. All right. However, so I just want to since I'm talking about the closer look of the implicit bias, so here's some additional synthetic experiment I run. And actually, the theorem tells that we do have the asymptotic convergence to the max margin direction, but actually the convergence is quite slow. So the directional or tangential error decays at the error rate of the 1 over log squared t, and the 1 over log squared t is extremely slow, just because we can just imagine. So if you are familiar enough with the convex optimization, since the optimization problem that we're considering right now is just like a logistic loss, which is convex. So typically it only decays in the 1 over t, which is way faster than at least that asymptotic directional convergence rate 1 over log squared t. So the theory tells that, we can just minimize the convex loss, but actually the implicit bias only happens in a quite later phase of the dynamics. But actually, is this really happening? We can just do the simple experiments by following all the setups that I showed you there. And we do have, here, I'm just doing the two-dimensional the experiment here. We have the first coordinate and the second coordinate of the parameters, and I'm just evolving the parameters like this. And the brighter, this is the parameter evolution following the gradient flow, but immediately goes to the the asymptotic direction like this, and we can just quantify this sort of the things by using the right-hand side, the plots. So you can just look at the first plot is just like a training risk, but the more important thing is that the second plot here. So the second plot just plots the degree of the asymptotic convergence. If it goes to the 1, so it means it already converges, and you can just see. I'm running in the bunch of the, this is really the gradient descent, the discrete time steps, but it immediately quickly goes to the almost near 1, the alignment. So actually this isn't captured by the theoretical, the 1 over log squared t, the convergence. So I was just interested into, can we show some sort of the earlier quick convergence to this asymptotic the direction? And this is what we did recently. So under the totally the same setups, we can just show that there is some problem dependent constant delta, such that for all delta, I'm writing the tangential error. This is just like a degree of the convergence to the asymptotic direction. If VT is close to 0, that it means it already converges to the the max margin directions. And this is small enough with only exponential, doubly exponential to the negative delta. So this just means, the convergence to this delta error of the directional convergence is pretty fast. But there's a small remark. So in the very first lines I just wrote, there exists a problem dependent constant delta bar, and the error tolerance, the term delta can be only allowed to be up to delta bar. So I mean, this delta cannot be arbitrarily small. If we allow delta to be arbitrarily small, then it recovers the asymptotic convergence, the previous result. But actually, since we only allow this convergence up to some problem-dependent constant, the bar delta, so we can just have this sort of very fast convergence up to some error tolerance. So the illustration is just like this. So we have the linear separator, true linear separator, the max margin linear separator here. And then the illustration is just something like this. So yeah, we're just looking at the tangential directional convergence. So just looking at the projection of the parameter on this hypersphere here. And let's say we're just beginning from the W0 here or the projected W0 here. And this convergence to up to some point is pretty fast, which is only like the W exponential negative delta. But the thing is that this radius of the convergence can be up to bar delta. And I'm not going to talk about the detail how large this the size of the convergence. But actually, after the careful computation, so we can just show this size of the convergence can be like the VT up to close to the square root of the gamma. Gamma is, again, this is a data set margin. And what is interesting here is that, yeah, actually, if you are familiar with the very classical half a century ago, the perceptron algorithm, the convergence analysis for the perceptron the algorithm is also shown to be shown under the linear separation assumption, and their convergence can be only up to gamma. But actually, so ours, or I mean the general logistic regression with the gradient flow can achieve the square root of gamma with a pretty fast convergence rate. And after achieving this convergence, then the asymptotic convergence is pretty slow after that. And it's just like this. So yeah, it's something, what I said, pretty the same things is just illustrated here. So after this, the fast convergence, I just said this is a weakly alignment. We can't achieve the perfect alignment, the VT close to 0 in a pretty fast time. But if we only allows the convergence up to the square root of the gamma, then we can just allow this convergence in a pretty W exponential time. And after that, so the convergence is pretty slow. And I think I have still like some of the time. So let me just briefly talk about how can we obtain this sort of the picture. So the very first step is to, since we're working on the directional convergence, so let us decompose our parameter WT to its radius component and the directional component. So RT denotes its norm, the radius component, and the UT denotes its directional component. And since we're working on the gradient flow, so we can just write down the differential equation for both RT and the UT like this. So this is very simply can be obtained expressions. And the term that target term that we are interested in was capital VT, which is I can just show you to make it sure again. So okay, so the capital VT is just like this, and it depends on the of course the W parameter WT. So after doing like a chain rule and so on, so we can just obtain the ordinary differential equation for this target quantity capital VT like this. So this can be obtained analytically. And after looking at this formulation, so we do have like, the two components here. So the blue rectangular the component here consists of the ratio of the loss function and the radius component. And both of them are can be evaluated pretty easily. This is a standard, nothing very new here. And this is just in the rate of the 1/t log t. So yeah, I mean, this is almost like a close to the end of the proof. But the only thing is that we have a second coefficient here, the inner product between something and something. And let's suppose that inner product is just like constant across all of the time. Then the ordinary differential equation for this capital VT is just like a the derivative equal to negative 1/t log t. So after assuming that is constant, then we can just solve this ordinary differential equation. Then everything is done. But the only thing is that we have to well control this second term here. So let me use about the 2 minutes to explain what is the second term here. So we have Z alpha and PU star or something. The Z is just basically the data sets here, and the alpha is exponentially weighting depending on the how large each point causes the error. So I think this is sort of quite similar to like a multiplicative exponential weighting in the online learning as well. So Z alpha is just basically, I illustrated here. So we have a bunch of the training data point here and doing the exponential, the weighting depending on the loss function here. So we obtain a Z alpha. And let's say the current parameter U is directs in that sort of the way, let's say, and we have the U star, this is the true separator here. And in this sort of the case, the second term, the P perpendicular U star, that is the orthogonal projection of the true separator U star to this, I mean, the parameter direction, just like this. So in this case, you can see after the projection, so we have the very close alignment between the Z alpha, I mean the exponentially weighted data points, and the projected true separator like this. But you can just see again, so this happens when the U and the U star directs in sort of the non-aligned other directions. So we do have the alignment very closely like this. But let's suppose if U and U star is very close enough, then, I mean, the projection of the U star to this, the orthogonal complement is just very marginal. And in this case, you see the inner product between the Z alpha and that one is pretty marginal. So that we no longer hope this term, this Z alpha inner product, this term is positive constant anymore, and that happens in the late stage of the dynamics. So we can just ensure the correlation between the exponentially weighted Z alpha and the parameter in the very early stage of the training. So that's what we are having here. All right. So that's almost all of the things I want to talk. But let me just mention a few more of the advancements in the recent years as well. So far we have been talking about the ordinal differential equation, the gradient flow setup, so which corresponds to the infinitesimal the step size here. And usually, of course, this is computationally not feasible. So what we do in the machine learning or the computational other things is that discretize the flow in the the discrete time setup, so which is the one of the view of the gradient descent. So actually, if we well control the step size eta to be like the smaller than inverse proportional to the smoothness of the loss function, then the approximation is really holds in a reasonable way to track the gradient flow like this. But such the well controlled learning rate is unfortunately, not very common in a deep learning setup. So just because the smoothness parameter is quite marginal in quite deep networks, and the people just use the eta, the step size, as usual step size in a very classical regime. So it obviously breaks the eta smaller than 1 or 2 over the beta, such kind of condition. And in such kind of condition, actually recall this is beyond the stability criteria. Stability criteria just means the eta is smaller than this inverse the smoothness here. And the people just call this as the edge of the stability, and some people just call like an EOS. And then this sort of the regime, so the parameter is bouncing quite a lot. And actually this doesn't guarantee the typical convex optimization guarantee. And in the classical convex optimization guarantee, let's assume the gradient descent is used and assume the capital L, the loss function that we use, is convex and jointly smooth, I mean the beta smooth. Then we can just ensure the convergence, 1/t convergence, as long as we use the nicely or control the step size. And it's very simple. After noting that we can just use a descent lemma, but I'm just going to skip here. But just because we're relying on the descent lemma, so the this well-controlled the step size is pretty crucial here. But actually, even beyond this, the eta smaller than 2 over the smoothness parameters, the nice convergence happens. Of course, this sort of nice convergence doesn't happen for the worst case convex functions, but in a practical, I mean, the interesting instances in the machine learning problems, this sort of the convergence still happens for some cases. let's say we're also considering the very totally the same setup, like a linearly separable logistic regression. And actually this, the loss landscape itself is pretty special for the edge of the stability. And we're not sure what sort of the structure will still persist beyond these setups, but actually this is one of the very nice things here. And we would all show such sort of the convergence. I mean, I'm only showing the numerical example here, but actually we do have a convergence in the worst case as well for this logistic regression. And we just sort of generalize this logistic regression to some other general loss function. And still we do have first, of course, since we no longer have a descent lemma just means every step time, so we're just decreasing the loss function monotonically. But this doesn't hold just because of our step size is quite large. So initially we do have a the oscillatory behavior here, but after for a while, so I mean, sort of the phase transition occurs, then it just enters the stable regime like this. So this is sort of the modified descent regime here, and that happens for the logistic regression and also as well as general the loss function here. Yeah, so that's just like something that I talk here. So even for such sort of the logistic regression, which seems to be a pretty classical, and we understood everything, but actually that's not the case in a dynamical regime like this. So we do have a non-trivial behavior for even like a gradient flow case, and also, I mean, the edge of stability. Such large step size regime is totally unexplored, and I think one of the quite exciting topics recently. So thank you very much.
Questions?
Thank you. Yeah, thank you for a nice talk. And I'm sorry if I missed something, but I mean about your like a fast convergence results, and there the delta appears. And my question is that how dimensionality affects this like a convergence speed. Like maybe dimension appears in the delta, but I just wondering how it affects.
I forgot how dimension comes into. Let me check and answer you later.
Okay, I see. Yeah, thank you very much.
More questions from the audience?
Oh, well, I can just answer quickly. So since our convergence depends on, thank you. Oh, I didn't write here, but actually the convergence rate also depends on the dataset margin gamma. So precisely speaking, this should be doubly exponentially negative delta over gamma square. So basically, the dataset margin can depend on the non-trivial, depending on the dimensionality. So I think the dimension dependency comes into there.
Okay, let's thank the speaker again.
Yes, so thank you for being here. So I'm gonna continue with some talking about gradient descent on neural networks. And in particular, I'm going to show some result that concerns the role of having temporal correlations among samples. So it's based on joint work, recent joint work with Dan Mikulincer from the University of Washington and Helkan Almosel from MIT. And the motivation comes from the fact that there is, of course, there's been a lot of works on the theory of neural networks to try to understand how the complexity of gradient descent. But usually most works belong to like two extremes. So the first extreme is the case where there is no statistical structure in the data. So it's like distribution-free guarantees. And the second extreme is like, the opposite, where there is an idealized stochastic structure in the data. And it is assumed that samples are taken IID from this idealized data distribution. And of course, there is an intermediate regime that is open, which is the one where samples are neither chosen adversarially, and they're also not independent, but they have some kind of structure correlations. So we focus on exactly this temporal axis of those correlations. They are relevant for several realistic domains, like computer vision or robotics. But I think what we are more interested here is in understanding whether, at least in some idealized settings, temporal correlations can reveal information that is not accessible under IID samples. So basically, they can reveal some information, some hidden structure of the task. And this is something that has been observed in other theoretical frameworks. But here we do study whether gradient descent on neural networks can exploit this extra information coming from temporal correlations. So the setting, the standard setting, the second extreme, so where we have a distribution D of the data where samples are IAD, in the supervised learning setup, which is the one that we focus on, samples come as pairs with a target function giving the labels. I'm going to assume no noise on the labels. And the goal is to understand, to learn this mapping F with a neural network. I'm going to focus on shallow networks, like the one in the picture, trained by standard gradient descent methods. So in the most standard definition. And the goal is, of course, after training, to have a network that at least on the same distribution as the training points approximates well F. And so I'm going to consider exactly this setting. So I'm going to keep this part unchanged, and I'm going to change this part here. So the IAD sampling. So the main message that of this talk is that indeed the gradient descent on neural networks can exploit this information containing temporal correlations, at least in some sparse tasks. The class of tasks that I'm interested in are Boolean tasks. So the input is going to be a vector of dimension D of just plus minus, each entry is plus minus 1, which is a good setting because, okay, it's of course mathematically tractable, and so it's it can give some, it allows us to isolate phenomena and study them rigorously. But it's also like rich enough to capture some bottlenecks of gradient descent learning and some phenomena that at least are observed in at least in tasks that have some discrete and combinatorial structure that is captured by this discrete input structure. I'm also putting another assumption, so I'm not going to study general Boolean functions. I'm going to study a specific class Boolean functions, which are called either sparse functions or Juntas. And those are functions that depend only on a subset of the coordinates that is small. So I'm going to assume that F depends only on a subset S of the D coordinates, and that S has cardinality K, and that K is small, so it does not grow with D. So just imagine, the input we have. Oops, sorry. The input is like, along a sequence, like for instance, this modular sequence of genes, but the task we are interested in, for instance, predicting a phenotype, depends only on a very sparse set of all these features. So like standard like subclass of these sparse functions are those called parities, those where F is just a single monomial. So just the product of all coordinates in set S. Again, S has small cardinality K. And these are called parities because xi are plus minus 1. So this product is, of course, plus 1 if the number of negative bits in S is even, and minus 1 if odd. So we consider this, if you consider learning these functions under IAD uniform input, so with no temporal correlations, then there has been some lower bounds that have been proven, at least for a version of gradient descent, which has, let's call noisy gradient descent, where the updates are population gradient plus Gaussian noise, so some idealized version of gradient descent. And on standard networks, the computational time that is needed to learn these functions is scales as d to the k, so like exponential in k. And the reason for like this hardness, like this can scale pretty badly if k is large, is that parities under the uniform distribution, they do not mean any low degree approximation. So if you look at the correlation under uniform inputs between our parity of degree k and any monomial that has degree strictly less than k, then this will have, we'll leave at least one spurious coordinate, and under uniform inputs will make this correlation. This correlation will be 0. So what this means is that when we learn these functions with gradient descent cannot gradually approximate these functions with learning like representations of increasing degree. It will have to learn all the coordinates like at once. And so it will basically perform similarly to a random search among all possible parities of degree k. And these are d choose k, which scales as d to the k. So this is for a uniform distribution with no temporal correlation. There has also been a matching positive result that has been proven on two-layer net that to the k that matches this this lower bound. And what we ask is, okay, what happens if now we are no longer IID? And okay, arguably like the easiest stochastic process we can think of the hypercube is a random walk. So I'm going to consider a p-lazy random walk where we start from uniform samples, so samples from a uniform distribution. And then at each step, we choose one random coordinate among the possible coordinates. And with probability p, we flip it. With probability 1 minus p, we just don't change. We don't change our input. So mathematically, this is it right here. We have zt is just a Bernoulli variable that with probability 1 minus p, nothing happens. With probability p, we flip the jt coordinate, which is chosen uniform inter-random. And what we ask is that are these like temporal correlations enough to bypass the t to the k barrier that we had with IID sampling? Okay, so the answer is that it can be enough if we push our network to look at to exploit like this temporal correlation. So we consider the temporal difference loss, which is a loss that has two terms. So the second one, this is just the standard square loss at time t. Whereas the first one is squared, basically penalizes the discrepancies between the increments between time t minus 1 at t, between the target and our network. So in other words, with basically we want to match both the value at time t on xt, but also the kind of the increments that we have between two consecutive samples. And alpha is like a parameter interpolates between the two. If alpha is equal to 0, then we have the standard square loss. If alpha is equal to 1, so if we had only this part, then the loss depends only on the finite difference, but then it would be invariant to constant addition to our target. So in other words, if we kept only the first term, then we would not be able to distinguish between basically any f plus c plus a constant would achieve 0 loss. So we do need to have both terms. So alpha can be close to 1, like this square loss term can be small, but alpha cannot be exactly 1. Otherwise, we don't identify correctly a function. We identify an invariant class. And I mean, it's already intuitive that this loss is convenient because like it's convenient to look at the increments because the increments, they contain a lot of information about the support, right? In particular, since our process is a random walk, this delta f of t, if at time t we flip a coordinate that is outside the support of S, then of course this delta f is 0. So in other words, this loss reacts mostly to changes inside the support. Okay, so then we can run some simulations. Here we are learning a parity of degree 5. And here I'm plotting the test accuracy, and this is just the length of the random walk, the number of samples in the random walk that we observe during training. At each step, we take like a batch of from this random walk consecutively. And we see that with temporal difference loss and random walk data, we learn much more efficiently than with the compared to the IID baselines. And so if we look at like a bit more about the representation learned by these orange curves, so the TD loss and random walk data. So here I'm plotting the Fourier coefficients, which are just the projection on the network on single monomials under the uniform distribution. And what I'm interested in looking here is at the projection of the network learns at the corresponding time on first order terms, so just single coordinates. And then looking at the difference, so this orange curve, this is first order information with a coordinate inside the support. So since the target is a parity over the first 5 coordinates, this is inside the support. this is first order information outside the support, and we can observe that there is some difference, at least in the variance between these two dynamics. So there is information, is not in the drift, but it's in the like kind of diffusive difference in the variance between these first order informations. This can be indeed exploited by gradient descent, and we can prove this result where if f is k-sparse functions, then if we do layer-wise SGD on a two-layer network, then we can learn with a number of samples that scales linearly in D and with the D square time. So this holds for any k-sparse function, in particular also for parities. And so if k is large enough, of course, this bypasses the D to the k barrier under IAD sampling. It is a uniform bound over all k-sparse functions. And yeah, the linear sample complexity, we believe it to be optimal. At least, we want to look at each coordinate at least once. And then what is hidden here is that inside these terms, the dependence, there is like a 2 to the k term. So the dependence of k is exponential, which means that this result is specific to sparse functions, so we cannot extend it to large k as it is. Okay. So the proof idea is the following. So before we looked at the correlation between f of x and some monomials of degree smaller than f. Here we're looking, if you want the same information, but on the increments. So we're going to look at the correlation between delta ft, and instead of looking single data points, we look at again increments also in the x's. And this is first order because we look at single coordinate, so here single xj. And under uniform inputs, this correlation here is 0. So there is no first order mean signal, so there is no first expectation signal. But there is information in the second order. So as opposed to the case without temporal correlation, with temporal correlation here we have that the second moment for coordinates inside the support is positive, whereas outside the support is 0. Which means that temporal differences, they introduce a support-dependent anisotropy that makes the support so then visible and prevents a gradient descent to do just a random search. So this can be exploited. So as I said, we trained layer-wise. So we first trained the first layer. And we can prove that after ordered these steps, then we can write the learned representations of the weights as basically a additive functional of the random walk. And these functions already has a difference in the variance. So for coordinates inside the support, it is noticeable variance, whereas outside the support it stays small. Here, for this part here, we need the random walk to be lazy because we need the ergodicity of the process. And then this information can be is enough to be exploited by the second layer training. So in particular, this difference in the variance is enough to have visibility of the support as also and also enough diversity. So actually, the difference this variance is actually pretty large. So we also have enough diversity so that all Boolean functions then can be recovered by the second layer. So if you look at other experiments, this is for instead of being for a single monomial as before, this is for still a sparse function, so a function that depends on 7 coordinates out of 50, but with multiple monomials. Again, with the temporal difference loss and random walk data, we can learn efficiently. And also, what is interesting is that here the support is all the coordinates in the function, they are picked at the same time. So in other words, it seems that it is, as our theoretical results suggest, really the support is picked. The lector first learns the support and then learns the correct function, other than learning first low degree terms, which at least could be the case in at least without those temporal correlations. So okay, this was for the temporal difference loss. If we look at standard losses, so by standard I mean single point losses. So where at each step we only have access to the difference between the target and the prediction on a single data point. for instance, square loss or any other standard loss. Then we can prove a lower bound, at least in the large batch size regime, which kind of emphasize the need of the temporal difference loss to obtain a positive result. So the lower bound is for, again, the noisy version of gradient descent with Gaussian noise injected with at each step. And for parity, at least, what the computational time that we need scales as this term here, which basically implies that we will need a lot of time, a lot of computation time, if k is large. So if this term here is small, since there is -1 here, and if the batch size also is large. And I think it could be quite intuitive to understand it. If we have a large batch size, then we cannot exploit the temporal correlations, because what gradient descent does is that just we take a chunk of the random walk of size of length b, and then we average the gradients over this path. And if like this chain is too long, then these averages will be close to stationary averages. And stationary averages for the random walk, the stationary distribution is just the uniform distribution. So in other words, we lose completely the information coming from the temporal correlations. And then if we, B has to be large, it's actually is enough to have B scaling quadratically with the input dimension, more than quadratically, so 2 plus delta, to have a performance that is suboptimal compared to the temporal difference loss. And again, so this is for large batch size. This lower bound does not cover the small batch size regime. So one can ask what happens if we have square loss, for instance, pointwise difference loss, and small batch size. And it turns out that at least according to some experiments, we can learn efficiently. So this is like the green line, and actually even more efficiently, or at least comparably, than with the temporal difference loss. So this is random walk data, and it's again for the parity of degree 5. And we suggest that indeed, it seems that in the small batch size regime, then we might be able to exploit the temporal correlations without the temporal difference loss. Then the theory is open for now. So to sum up, we study how to learn k-sparse functions with SGD on random walk data. The picture is the following. So with temporal difference loss, we can prove efficient learning with linear sample complexity. This is also for large batch size, at least as large as D. With the square loss and large enough batch size, then we can prove hardness. Whereas there is this regime that is open, that might be where at least efficient learning might be possible according to experiments, which is for square loss or like pointwise losses and the small batch size. So for future work, other than understanding the role of the batch size for exploiting these correlations, also of course random walk is a stylized and a kind of specific model for temporal correlations. It would be interesting to analyze more general models. Okay, thank you.
Yeah. There's time for questions. Yes.
Thanks. This is amazing work, I think. So in my understanding, so your improvement with that noise model is to add a new extra term in the loss function instead. In addition to this square loss, right? Yeah, so I just I'm interested in, just because this is sort of the, once we do have this sort of the noise model, then we can just adapt our objective function to this noise model. So that my question is something like whether this loss function is quite tailored for this the noise model, or is more sort of the natural one, or it's kind of the broader question. I mean.
Yeah, so let me say first, one thing that I haven't said is that we need this temporal difference loss and also random walk data. Like if we trained on IAD data with this loss, we would still fall in the D to the K barrier. So first of all, we need the two. Then whether we need this, okay, with small batch size, for instance, it's possible that we don't need it. And whether there are other ways to look at temporal correlations, yes, it's possible. You can. Yeah, I mean, I guess here you can. We took like the square loss. You could take anything, any other like things that penalize the basically difference in the increments between labels and like absolute value, I don't know, whatever. Yeah, I think yes, it was natural to take the square loss of the increments, but it can be anything else.
I mean,
right in the chat. Okay, wait, let me. I'm gonna
you
see.
can see.
Okay, I'm not sure I'm familiar with these existing results.
There's one more. There's one more.
In the limit.
Reveal. I need to be in a quiet room because it's in the middle of the night. This probably doesn't want to wake up other people.
So I'm not sure I understand so the smoothie connect.
Moving probability going to zero, the random walk stops walking.
So just
the
so from some
probability
point on,
going to zero. Yeah, the probability.
From some point on, we just receive the constant data, or the temporal dependence goes to zero.
I don't know.
Because if we receive constant data, I mean, depends whether we observed enough diversity of the data. If we observe at least these samples, and then these are enough to learn the function, so then whatever we observe, I mean, this is noiseless label, so there is no overfitting. Then, I mean, for us, P is fixed, and it's only P, the laziness is fixed.
So it becomes stationary. The random walk becomes.
So it becomes stationary again. So I think it can become stationary. So I think you need at least D samples where you can exploit these temporal correlations.
Okay.
At least to be able to learn any. Yeah. Sorry. Like,
there's one more.
Can you show the slide of the definition of P? Yes, this I can do. This one. Okay, so P is the probability of moving. So P cannot be 1. We cannot move at each step because otherwise we don't have ergodicity. This is like a technical.
Yeah, there is no stationarity here.
Yes, it's going to be like converged to the stationary distribution after roughly D steps D over P. So.
No, sorry, because it's all the hypercube. Okay, yes. So it's uniform. It's uniform.
Converged to stationary distribution. The limit of P that goes to 0. So P goes to 0 means that at some point I just stop moving.
Yeah, you stop taking samples.
Yeah. So again, this is. I mean, it depends whether, at least if we have enough, if P goes to 0, like and we have seen enough diversity, at least order D samples, then this should be enough. If P goes to 0 before, yes, then this can complicate things. But I don't know whether there is, like, we haven't studied a dependence on the complexity on P scaling, so I don't know. In the intermediate regime, I don't know how it depends. I hope I answered the question.
But so the result doesn't depend on P. That doesn't.
It does seem to be constant. Yes, it's D over P.
It's like D over P. Yeah. Okay.
Yeah. Sorry. That. So there is a dependence on the P is kept fixed. Yes.
Pick it a half.
Because it depends on the spectral, like the convergence.
Yeah.
I think maybe that was the question. Yeah.
Cool. Thank you.
Non-technical question.
Huh?
So you focused on K sparse function, right? Parity function.
Yeah.
So,
yeah.
So, like, how realistic is it to consider that function? Simulations are also following that setting, and yeah, it's nice that theory can predict the behavior. But in the end, you want to explain the behavior of real neural networks, right?
Yeah. So that's a fair question. I think it could be relevant if you want to learn some. Like the idea is that this temporal correlation allows to learn to break some symmetry that you have in the targets, which is here kind of this what gives you the D to the K bottleneck. So this symmetry can happen in some like logic data set where data set like where you do have some kind of hardness there. It's possible that it also helps in more general case when you have sparsity, even without this specific, because here you have both the sparsity and also the uniform distribution, which are two specific things. It's possible. I would expect it in general they help in cases where you have intrinsic hardness coming from some symmetry. So yeah, I don't know how.
Okay, thank you.
Thanks again.